A Brief History of Time, written by Stephen Hawking, read by Akashveer. This is chapter number 8, The Origin and Fate of the Universe, Part 2. This picture of a universe that started off very hot and cooled as it expanded is in agreement with all the observational evidence that we have today. Nevertheless, it leaves a number of important questions unanswered. Question number 1. Why was the early universe so hot? Why is the universe so uniform on a large scale? Why does it look the same at all points of space in all directions? In particular, why is the temperature of the microwave background radiation so nearly the same when we look in different directions? It is a bit like asking a question of students, an exam question. If they all give exactly the same answer, you can be pretty sure that they have communicated with each other. Yet, in the model described above, there would not have been time since the Big Bang for light to get from the distant region to another, even though the regions were close together in the early universe. According to the theory of relativity, if light cannot get from one region to another, no other information can. So, there would be no way in which different regions in the early universe could have come to have had the same temperature as each other, unless for some unexplained reason they happen to start out with the same temperature. Question number 3. Why did the universe start out with so nearly the critical rate of expansion that separates models that recollapse from those that go on expanding forever, so that even now, 10,000 million years later, it is still expanding at nearly the critical rate? If the rate of expansion 1 second after the Big Bang had been smaller by even 1 part in 100,000 million, the universe would have recollapsed before it ever reached its present size. Question number 4. Despite the fact that the universe is so uniform and homogeneous on a large scale, it contains local irregularities, such as stars and galaxies. These are thought to have developed from small differences in the density of early universe from one region to another. What was the origin of these density fluctuations? The general theory of relativity on its own cannot explain these features or answer these questions because of its predictions that the universe started off with infinite density at the Big Bang singularity. At the singularity, general relativity and all other physical laws would break down. One couldn't predict what would come out of the singularity. As explained before, this means that one might as well cut the Big Bang and any events before it out of that theory, because they can have no effect on what we observe. Space-time would have a boundary, a beginning at the Big Bang. Science seems to have uncovered a set of laws that, within the limits set by the Untitled Principle, tell us how the universe will develop with time. These laws may have originally been decreed by God, but it appears that He had since left the universe to evolve according to them, and does not now intervene in it. But how did He choose the initial state or configuration of the universe? What were the boundary conditions at the beginning of time? One possible answer is to say that God chose the initial configuration of the universe for reasons that we cannot hope to understand. This would certainly have been within the power of an omnipotent being, but if He had started it off in such an incomprehensible way, why did He choose to let it evolve according to laws that we could understand? The whole history of science has been the gradual realization that events do not happen in an arbitrary manner, but that they reflect a certain underlying order, which may be or may not be divinely inspired. It would be only natural to suppose that this order should apply not only to the law but also to the condition at the boundary of space-time that specify the initial state of the universe. There may be a large number of models of the universe with different initial conditions that all obey the laws. There ought to be some principle that picks out one initial state and hence one model to represent our universe. One such possibility is what are called chaotic boundary conditions. These implicitly assume either that the universe is spatially infinite or that there are infinitely many universes. Under chaotic boundary condition, the probability of finding any particular region of space in any given configuration just after the Big Bang is the same in some sense as the probability of finding it in any other configuration. The initial state of the universe is chosen pure randomly. This would mean that the early universe would probably have been very chaotic and irregular because there are many more chaotic and disordered configurations for the universe than there are smooth and ordered ones. If each configuration is equally probable, it is likely that the universe started out in a chaotic and disordered state, simply because there are so many more of them. It is difficult to see how such chaotic initial conditions could have given rise to a universe that is so smooth and regular on a large scale as ours is today. One would also have expected the density fluctuations in such a model to have led to the formation of many more primordial black holes than the upper limit that has been set by the observation of the gamma radiation band. If the universe is indeed spatially infinite, or if there are infinitely many universes, there would probably be some large region somewhere that started out in a smooth and uniform manner. It's a bit like the well-known hoarded monkeys hammering away on typewriters. Most of what they write will be garbage, but very occasionally, by pure chance, they will type one word of Shakespeare's sonnet. Similarly, in the case of the universe, could it be that we are living in a region that just happened by chance to be smooth and uniform? At first sight, this might seem very improbable because such smooth regions would be heavily outnumbered by chaotic and irregular regions. However, suppose that only in the smooth regions were galaxies and stars formed and were conditions right for the development of complicated self-replicating organisms like ourselves, who were capable of asking the questions, why is the universe so smooth? This is an example of the application of what is known as the Anthropic Principle, which can be paraphrased as we are the universe the way it is because we exist. There are two versions of the Anthropic Principle, the weak and the strong. The weak Anthropic Principle states that in a universe there is large or infinite in space and or time. The conditions necessary for the development of intelligent life will be met only in certain regions that are limited in space and time. The intelligent being in these regions should therefore not be surprised if they were observed that their locality in the universe satisfies the conditions that are necessary for their existence. It's a bit like a rich person living in a wealthy area or seeing any poverty. One example of the use of the weak Anthropic Principle is to explain why the Big Bang occurred about 10,000 million years ago. It takes about that long for intelligent being to evolve. As explained above, an early generation of stars first had to form. These stars converted some of the original hydrogen and helium into elements like carbon and oxygen, out of which we are made. The stars then exploded as supernova, and their debris went to form other stars and planets, among them those of our solar system, which is about 5,000 million years old. The first 1 or 2,000 million years of the Earth's existence were too hot for the development of anything complicated. The remaining 3,000 million years or so have been taken up by the slow process of biological evolution, which has led from the simplest organisms to beings who are capable of measuring time back to the Big Bang. Few people would have quarreled with the validity or utility of the weak Anthropic Principle. Some, however, go much further and propose a strong version of the principle. According to this theory, there are either many different universes or many different regions of a single universe, each with its own initial configuration and perhaps with its own set of laws of science. In most of these universes, the conditions would not be right for the development of complicated organisms. Only in the few universes that are like ours would intelligent beings develop and ask the question, why is the universe the way we see it? The answer is then simple. If it had been different, we would not be here. The laws of science as we know them at present contain many fundamental numbers, like the size of the electric charge of the electron and the ratio of the masses of the proton and the electron. We cannot at the moment at least predict the values of these numbers from theory. We have to find them by observation. It may be that one day we shall discover a complete unified theory that predicts them all. But it is also possible that some or all of them vary from universe to universe or within a single universe. The remarkable fact is that the values of these numbers seems to have been very finely adjusted to make possible the development of life. For example, if the electric charge of electron had been only slightly different, stars either would have been unable to burn hydrogen and helium, or else they would not have. Of course, there might be other forms of intelligent life, not dreamed of even by writers of science fiction, that did not require the light of stars like the sun or the heavier chemical elements that are made in the stars and are flung back into space when the stars explode. Nevertheless, it seems clear that there are relatively few ranges of values from the numbers that would allow the development of any form of intelligent life. Most sets of values would give rise to universes that, although they might be very beautiful, would contain no one able to wonder at that beauty. One can take this either as evidence of a divine purpose in creation and the choice of the laws of science, or as support for the strong anthropic principle. There are a number of objections that can raise to the strong anthropic principle as an explanation of the observed state of the universe. First, in what sense can all these different universes be said to exist? If they all are really separate from each other, what happens in other universes can have no observable consequence in our own universe. We should therefore use the principle of economy and cut them out of the theory. If, on the other hand, they are just different regions of a single universe, the laws of science would have to be same in each region, because otherwise one could not move continuously from one region to another. In this case, the only difference between the regions would be their initial configuration, and so the strong anthropic principle would reduce to the weak one. A second objection to the strong anthropic principle is that it runs against the tide of the whole history of science. we have developed from the geocentric cosmologies of Ptolemy and his forebears, through the heliocentric cosmology of Copernicus and Galileo, to the modern picture in which the Earth is a medium-sized planet orbiting around an average-sized star in the outer suburbs of an ordinary spiral galaxy, which is itself only one of about a million galaxies in the observable universe. Yet the strong Anthropic Principle would claim that this whole vast construction exists simply for our sake. This is very hard to believe. Our solar system is certainly a prerequisite for our existence, and one might extend this to the whole of our galaxy to allow for an earlier generation of stars that created the heavier elements. But there does not seem to be any need for all these other galaxies, nor for the universe to be so uniform and simpler in every direction on the large scale. Thank you very much for watching. If you want some more videos like this one, please like, share and subscribe to my channel. Have a great day. Stay home. Stay safe.